Welcome! Today we're going to break down one of the most fundamental concepts in electrical engineering, something that directly impacts efficiency, cost, and the health of the entire system, power factor.
All right, here's how we're going to tackle this. First, we'll get the basics of AC circuits down. Then, we'll see how to actually visualize what's going on with phasor diagrams. From there, we'll quantify it all with the power triangle. After that, we'll get into the real-world problems that a low power factor causes, show you exactly how to engineer the solution, and then wrap it all up with the key takeaways you need for your career. So let's start at the very beginning, in this invisible world of alternating current. Unlike DC, AC isn't just a steady, constant flow. Nope. It's more like a constant rhythmic dance, where the voltage and current are always changing, rising and falling in these smooth sine waves. Now, in a perfect world, if you just had a simple load, like a basic heater, what we call a purely resistive load, then the voltage and current waves would be perfect dance partners. They'd be totally in sync. They peak together, they hit zero together, everything's great. But as you've probably figured out, the real world is almost never that simple. You see, most of the real heavy equipment you'll find out on site, we're talking motors, transformers, that kind of stuff, they're what we call inductive. It takes a little bit of energy to get their magnetic fields going, right? So because of that, the current actually falls behind the voltage. It lags. On the flip side, you have capacitive loads. They're less common, but they do the exact opposite. They cause the current to get out in front, or lead the voltage. And this out-of-sync relationship, that is the absolute core of what power factor is all about. So trying to figure out what's happening in a circuit by just staring at two overlapping sine waves, it's a massive headache, it's confusing. So engineers came up with a much smarter way to simplify it all, the phasor diagram.
Just think of a phasor as a snapshot, a freeze frame of a spinning arrow. It brilliantly captures the two things we care most about, how strong the signal is and what its phase angle is, all in one simple picture. And just like that, you've turned a messy wave problem into some straightforward geometry. So much easier.
And this shows it perfectly. So on the left, you've got a basic circuit for, say, a motor. It's got a resistor and an inductor. Now, look at the phasor diagram on the right. That source voltage line is our reference, pointing straight out. But see the current vector, the one labeled I? It's pointing down, lagging behind the voltage. That angle between them, that's the phase difference, and it's the root of all our power factor problems.
Okay, so now that we can actually see this phase difference, let's talk about how it impacts the power flowing through your system. And this is where we get to probably the most important concept in this whole explainer, the power triangle.
First up, we've got the power that we actually want, the good stuff. It's called real power, or P. This is the energy that's doing useful work, turning the motor shaft, lighting up the bulb, creating the heat. It's measured in watts, and it's what you're actually trying to accomplish.
Then you have reactive power, or Q. Now this is the power that's needed to build and sustain the magnetic fields in things like motors. It's a necessary evil, you could say. It doesn't do any real work itself, but it's essential for the equipment to run. Just think of it as power that's constantly sloshing back and forth on the wires, taking up space, but never actually getting used.
And finally, there's apparent power, S. This is the total package. It's what the utility has to actually generate and send down the lines to satisfy your need for both the real power and that sloshing reactive power. It's the whole shebang, measured in volt-amps.
And here's the beautiful part. These three types of power, they form a perfect right-angle triangle. You've got real power as the base, reactive power going up the side, and apparent power as the long hypotenuse. This simple triangle is maybe the single most important visual for understanding and managing electrical efficiency.
So the bottom line is, we can take this whole relationship and boil it down to a single, really powerful number. And that number, the power factor, tells you exactly how well you're actually using the total power being sent to you.
You know what? Here's the best way to think about it. Think of a glass of beer. The apparent power? That's the whole glass. The real power is the actual beer, the part you want to drink. And the reactive power? That's the foam on top. It takes up space in the glass, right? But it doesn't do you any good. So power factor is just the ratio of beer to the total glass. A power factor of 1.0 means you've got a full glass of beer with zero foam. Perfect efficiency.
Okay, so what actually happens when that power factor number is low, when you've got too much foam in your glass? This isn't just an academic thing. As an engineer, understanding this is where you can make a massive financial and operational impact for your company.
Look, a low power factor has serious, real-world consequences. Utilities, especially here in Australia and New Zealand, will smack you with penalty charges for it.
Why? Because they're having to supply all that extra reactive current and it's just clogging up their network. It means your own transformers and cables are running hotter, wasting energy, and you have less capacity for actual useful work. It could even cause voltage to drop, which can damage sensitive equipment. It's just inefficient, it's expensive, and frankly, it's wasteful.
But, and this is the important part, here's the great news. This is a totally solvable problem. And designing the fix, what we call power factor correction, is a core skill that makes you an incredibly valuable engineer. This is where you get to be the hero.
This strategy is actually kind of genius. Our inductive loads, like motors, they need that reactive power to work. So instead of making the utility pump it all the way from the power station, clogging up the whole grid, why don't we just make it right there on site, right next to the machine that needs it?
And our tool for the job is the capacitor bank. Remember how we said inductive loads make the current lag? Well, capacitors do the exact opposite. They make the current lead. So when you put them together, they cancel each other out. The capacitor basically supplies that reactive power locally, keeping the motor happy. And the utility is happy because now all they have to send to you is the good stuff, the useful real power.
So here's your before picture. The source, the grid, has to supply the whole package deal, that big apparent power. It's sending the useful real power, sure, but it's also sending that huge chunk of reactive power the motor is demanding. Our power triangle is really tall and inefficient.
Now, check out the after picture. We've added a capacitor right there next to the load. And look what happens. It's supplying most of that reactive power locally. The real power, P, is exactly the same. We're still doing the same amount of work. But look at the reactive power Q that the utility sees. It's tiny now. That shrinks the total apparent power, S, and our power factor gets way, way closer to that perfect 1.0.
All right, let's wrap this up. If you forget everything else from this explainer, just try to keep these essential points in your back pocket. This is the stuff that matters day to day.
Okay, so at its heart, power factor is all about efficiency. Working power divided by total power. The number one problem you are going to see over and over is a lagging power factor caused by motors. Just remember, low power factor costs real money, it wastes energy, and it eats up the capacity of your electrical system. And your superpower is knowing that you can fix it, usually with capacitor banks right at the source of the problem. Being the engineer who can spot this and solve it, that is a high-value skill, believe me. So now I want you to take this knowledge and actually use it. Think about your own environment, that industrial plant you work at, the commercial building you're in, the network you're designing. Start asking yourself, where are my motors? Where are my transformers? Where's all that inefficiency hiding in plain sight? And where is the biggest opportunity for you to make a real difference?